to R4, so that the image is transverse to the radial Lula vector field. Then that's how you get the corresponding contact form on S3. I think you do something which is fairly standard if you were raised on subductive field theory, right, which is this idea to stretch the neck. So what we want to do is, let's see. So for me, this is going to be CP2, and here we're going to have this CP1 at infinity. And then, as it turns out, okay, so I guess I can draw this right here. This will be our embedded S3 sitting inside there. And we had this result when we had this result. So we had this result in 1985. It says, okay, put, you have the Fubini study metric on CP2, and if you use that to tame any almost complex structure on CP2, then there exists a unique degree 1 embedded pseudo-holomorphic sphere, which passes through any 2 points you might like. So you sort of get a foliation of CP2 away from the CP1, where you have 1 point where all your leaves intersect. And the interesting thing then is if you do this next metric construction, where we take a neighborhood of this S3 and we stretch it, we make it very long, we still have our CP1 up here, and we make all these conditions on our almost complex structure. We had conditions like, let's see, the J applied to the vertical direction is the ray vector field, and we want the J to be translation invariant in this region here. We can define C to be equal to the kernel of lambda, which is our contact form, and we want J to map the C to itself, and we want it to be the case that if we look at D lambda restricted to C, then this 2 form here becomes positive, definite, or tensor rather, and symmetric. So I think these are all our conditions. And then at the end of this process, right, so the idea is we take this region, we stretch it open. Oops, should do that further. And so at the end of this process, you have, for instance, just trying to draw this. I'll have a picture which makes sense if you've seen the stuff before, and maybe not much sense if you haven't. But the idea is that you now have some pseudo-holomorphic curves, then which have some negative end out here, I suppose I should say. Pseudo-holomorphic curves, a map of the surface into, in this case here, well, we can sort of say an almost complex manifold, so that it intertwines the almost complex structure on a target. So you look at the image of these, and you end up with pictures which sort of look like something like this, maybe. But you stretch the neck, and as it turns out, for any one of the almost complex structures that you put on this case, you can sort of squish this region down here together, embed it back into CP2, and the corresponding push forward of the almost complex structure will still be omega tame, and therefore Rowland's result applies, so that in this picture here, as you stretch the neck, you still end up with these sort of curves which have to sort of run through this region. And then you fully stretch the neck, and you get something which I'm trying to draw out a little bit more here, where you have some sort of holomorphic curve which sort of intersects some component which in the top, some component of a pseudo-holomorphic curve in the topmost piece, which has a negative end, and then we have in this region here we have R cross, in this case S3, and we have some pseudo-holomorphic cylinder, and then down at the bottom we have another pseudo-holomorphic piece which is correspondingly asymptotic in the positive direction. And it's asymptotic to sort of the usual orbit cylinders. So I'm sort of going to assume that people are somewhat familiar with this, so they don't need to go over too many details. But what I want to argue is that there's a key feature of the contact case, right, which is the case that we're sort of describing at this point here, which is that we have automatic energy balance. So in the HWZ language, there's a definition of energy that I don't like, so I'll change it, but it's equivalent so this is my definition of energy, and I'll describe it somewhat geometrically here in a second. Right, the idea is that as long as you're only considering curves, you say for instance, the Gromov degree 1 spheres, for instance, then this quantity as you stretch the neck will always be bounded uniformly, independent of which curve you pick, and independent of everything else. So this, geometrically, how do I think of this? I should mention that Taub sort of thinks of energy on pseudo-holomorphic curves in kind of a similar way. The idea is that you have sort of, you have a positive puncture which is asymptotic to an orbit cylinder, you have a negative puncture which is asymptotic to an orbit cylinder, and then what you do is you pick out this interval here. So we're kind of thinking of, this direction here is M, and this direction here is R. And so what we do is we pick out this interval here. We thicken up a level set. This becomes A naught, comma A naught plus 1 across M. And then I kind of ask the question, how much, well, I would say how much area does your curve have in just this region? And as it turns out, if you take this 2 form and semi-compose with an almost complex structure, you do get a Riemannian metric. And so in fact, this is computing area for you, or rather pullback area. And so what we're asking is that the amount of area in this sort of thickened slice is independent of sort of where you, but not independent, is bound from above, uniformly independent of where you put that slice relative to your curve. So then we say, please please.
Well, you have to limit energy is just global energy is cosmological, so that's uniformly bounded. But then you have to limit it, you can only bound it on every.
So what I would say is if you use Helmut's, I think it's Helmut's definition of energy, then essentially what you're doing is you're saying, let's see, before you stretch very far but not all the way, and then what you're doing is you're sort of pushing it forward into CP1, and then you're just integrating sort of the omega on, in CP2, and you're just integrating this omega on some sort of slightly thickened portion. And of course, because the symplectic form evaluates positively on complex lines, you get something which is bounded from above in terms of, it's cohomological, bound from above is cohomological. And what happens is if you use that same formulation, if you use Helmut's same formulation, then that idea sort of carries over essentially just fine. If you use my formulation, you put an extra constant in there, right? You'd say something like, there's I want to say.
Now you take that slice, then make it larger, and you can take the symplectic form up to your Swiss and up to there as well, and then you can have different ways how to get from there to there. The symplectic form you want to talk about. In particular, you go very flat, and then has a bar here. And wherever you put that bar, you get that estimate.
Yeah.
So you estimate it, actually, the right way to do it is you study this general of the curve with essentially a large family of different symplectic structures, which outside the trajectories of things, but inside you take all kinds of different things.
Yeah, that can be done. I don't like any of this approach, though. So for me, of course, as I started working on the analysis here, what's most important to me is that I have a fixed metric, and I want my metric to be translation invariant, for instance, right? That's going to allow me to do certain amount of analysis. And so from that perspective, it makes way more sense for me to take a definition like this as energy, right? Because everything I do is relative to that Riemannian metric that you get, which is sort of automatic once you have your contact form or your stable or even your Frank Hamiltonian manifold together with an almost complex structure. Kind of comes for free. And so my attitude was like, okay, let's just make use of this from sort of square one and try and step away from sort of the symplectic perspective, because staying in the sort of symplectic frame of mind here, I think it just disaster happens pretty quickly, and so you kind of have to step away from that, or at least that's what I thought. That's how we make progress.
So I think at moments now it seems to be that omega is an important thing, and then you take a J zero structure. But I think when you start to study contact, you should actually take the J, a lot of different symplectic structures compatible with it, then you form a vector. So you have one vector of symplectic structures controlling exclusively chosen. So that's a chip. That's a chip that we use further.
Yes. So again, just to sort of reiterate, you've got CP1, as long as you have an omega-tamed almost complex structure, you have this sort of near foliation of isomorphic embedded spheres, the only singular point of infinity where it's not a foliation. And then you do this next version construction, which has some translation invariant almost complex structure, suitably adapted. But if you do that, then you can always take this, squish it into here, and the push forward of your almost complex structure is tame, and so consequently you get your spheres, you move back in this picture and then stretch all the way, and then see what shows up in the limit. And what shows up in the limit is you'll have pseudo-holomorphic curves which have this positive end, and some work then shows that the positive end you have to be asymptotic to an orbit cylinder, you found your periodic orbit, you're done. So this has been around for quite a while, and so now we have a crazy idea. Replace the tight S3 in CP2, so anything sort of star-shaped, with an arbitrary closed hypersurface. Does the same argument work? I mean, in some sense you might say, well, it seems kind of plausible, right? I mean, maybe we can sort of adjust this thing so we have, again, almost complex structure, sort of translation invariant. We have to adapt sort of slightly different because instead of having a contact form now, you have a stable framed Hamiltonian structure. So this is a closed 2 form on your hypersurface. It has kernel, and then this is sort of this provides the framing on your kernel. And so this is a 1 form. And so this pair is the sort of gadget that you get instead. And so you might say, well, maybe the same thing, the same idea works. So maybe it works, but then there's reality, which says nope. And let's see. There's a theorem by Ginsburg and Rao, which says that there exists a proper C2 Hamiltonian on R4 such that H inverse of 0 is diffeomorphic to S3, and it's a regular energy level, and has no periodic orbits. By it having no periodic orbits, I mean the associated Hamiltonian flow has no periodic orbits. So, then comes the bad news. No, let's see. Yeah, they explicitly show that there's no periodic orbit. Or explicit enough.
Just sort of it's their own question that you can find it.
Yeah, that's not known.
Then they claim they can bring it up to C2 plus alpha, which actually has some meaning. C2 electrons can become alpha molecularity really difficult.
Yeah. So there's kind of a hidden plus epsilon here. They claim that the techniques that they use should carry over. There should be no instruction to increase in the regularity slightly. But they don't, I think, presumably because this is sort of good enough, I think, for this case. So right, so we have this idea, maybe we can stretch and find periodic orbits, but we sort of have this example modulo, this sort of regularity issue. We have an example of an energy surface which is S3, but has no periodic orbit. So that seems bad. So then the idea is to say, okay, this is the standard, I think, hope for follow-up, which is, well, what goes wrong? We seem to have this nice idea, right? It seems like it should work. We have strong reason to believe it's not going to work. So why not? So, and the preliminary answer is that there's instant loss of energy bounce. So what I said, see if I still have it here, is, yeah, here it is. A key feature of the contact case is that you automatically have these energy bounds. Where I describe the energy in this way, in particular, the way I like to think of it is that in some thickened slice, there's a bound on how much area I have, how much area the pseudo-Hellman curve has in this region, and that bound is independent of where I take that thickened slice, up or down. So what that means then, necessarily, is as a consequence essentially of this, is that now, as you try and do this next stretching, you lose this bound. You lose an a priori bound on your energy, and that means that as you slide around up and down, there's going to be places where the area of the portion of the curve blows up and goes to infinity. Now, I think generally speaking in the field, I think the sign is relevant. If you don't have energy bounds, you don't have much of anything. No energy bounds destroys so much of the standard analysis, pretty much everything, right? So, ye who enter. Ye who enter here. Yes. Dante's Inferno? No. So. So let me try and give a picture, a description of it, to kind of give some idea of how weird this is. And that's kind of what got me started really thinking was that I just got stuck, right? This idea that, you know, what happens when you lose that energy bound? Like, what's going on? Or what could be going on? So here's sort of the top end, and maybe imagine that you fully stretch the net, right? And if you do that, then you still have the CP1 that's sort of hanging around here up near infinity. So it's going to foliate out some sort of nice, some nice moduli space over here, signaling foliate here. You're going to have some curves, and then as you progress, like those curves are going to sort of start to dip down into this negative end, right? So what happens? You know, so I'm going to change this a little bit. So if you dip down, so this path here is going to represent something like a sphere. So this is my minimum, and this is sort of my maximum in some appropriate sense, right? And then the idea is that, you know, you have some family, and they're going to dip down further and further into this region down here. What happens, maybe? Well, you start thinking about it, and right, maybe something like this happens. The squiggliness here, so we see length, so we should think area, and the idea is that in any sort of thickened region here, as you progress through this family, as these curves dip further and further down into this region, it's the case that the length is sort of larger and larger, which we're supposed to think of as the area, or the energy getting sort of larger and larger and larger as you might like. So this can happen. And this just looks absolutely disastrous. And so you think, okay, so nothing can be done. And what bothered me most about this picture, I mean, in some sense, you think about it, and something like this, in some sense, has to happen. Because we have Ginzburg-Gorel. We imagine it can be sort of souped up to the smooth case. Something like this has to happen, because if it didn't, we'd have a periodic orbit. Okay.
So even that is not theoretical. What the equivalent of your previous stable wheel structure, whatever, where you have finite energy, then that means that you're converging to some periodic orbit at infinity, like do you not contact type, then it's unclear what finite energy means, or is it?
So finite energy is erased. But my notion of energy now in this case, so what happens is on any given hypersurface here, you still have an omega, right? Right?
But it's not a 5 times.
It's not just the 2 form on the hypersurface.
It's the 2 form on the hypersurface, yeah. And so the idea is that now you have something called a framed Hamiltonian structure, right? Where lambda wedge omega is a volume form on your hypersurface, right? On your hypersurface, this is a 2 form with kernel, and then I can make this non-zero in the kernel, and that's going to give me a volume form on M. And so consequently, and then you can still think of this, the kernel of this guy here will still call C. It's not going to be a contact structure anymore, but it's still a 2-plane distribution. And then I can make J sort of maps C to C, and I can still require, for instance, that omega restricted to C, that this is again symmetric, positive, definite. And then consequently, on this R invariant region, then I can talk about an energy, which is again this sort of supremum over sort of all shifts. So the integral of, let's see, A naught comma A naught plus 1, A sort of U inverse applied to this. This is U star, dA wedge lambda plus omega. And this 2 form right here is translation invariant. It evaluates positively on complex J complex lines. And so we just sort of add it up, and I look at this, and in fact computes area if we look at the corresponding symmetric bilinear form. And so this is sort of a reasonable notion of energy, and this is what blows up. Okay?
But it only goes on because of the dA wedge lambda.
Yeah, so that's also important. So because this omega arises essentially as you pull back. So usually we think of there being an omega on the whole symplectic space, which you would write little omega, and I want to write just to sort of separate it out capital omega, right? And so we restrict capital omega to our hypersurface, we get little omega, and consequently, yeah. So you can look at just a little omega energy, and that will be bounded. So you think, so that in fact that's sort of an important, a really important point, is that you do have these a priori bounds.
Yeah, that's
not close to that.
That's part of the point. Yeah, it's closed, and it's also the case that it evaluates non-negatively on J complex lines, and it also sort of fits together with you can sort of it fits together with sort of in some sense it adds up to your capital omega as well.
So it's not a context that you still have the transversal control to the vector field.
Yeah. So the idea here, the way I think about this is, let's see. The way I think about this is this C is kind of area, sort of vertical area, right? Subplexization direction maps to the rim, and then your omega term kind of measures sort of horizontal area.
So your picture is actually something like this.
So yeah. So in some sense, maybe it's actually. So we can actually be really more precise. What happens essentially is if this is the subplexization direction and this is M, then it wraps around in these big sheets. And so what happens is if you look at each individual level set of your pseudo-holomorphic curve and you think of a movie as you sort of slide up, you have these loops, and the loops get longer and longer and longer and longer, but they do so very, very slowly, very, very slowly. So your corresponding tangent planes to your pseudo-holomorphic curve, they become sort of more and more vertical. It looks like it's sort of wrapping around and around, and this gives you some idea of sort of the best way, in fact this is the way, you lose energy bound. Any other questions so far?
But in some sense, though, anything that was saying sort of locally, like, I don't know, is it really each and every component, if essentially the little has rapid energy?
That's the key. That's the key. That's one of the major components of the paper, right? Is establishing that in fact is true. Before we get there, though, there's something I want to highlight this because there's a couple of key insights into this problem. So I want to tell you the first one, and then the second one is exactly what Barney alluded to, which is that if you think about sort of how bad, and this is one of the ways I sort of like to think about things. You sort of imagine, how bad could it get, and then try to find the weirdest feature that just doesn't sit right with you, and build off of that. And for me, I said, okay, we know it has to be the case that sort of the energy kind of blows up. What's the weirdest feature about this that I just thought this cannot possibly happen, right? And the weirdest feature for me was to focus on that absolute minimum. Is it the case that if you focus on the absolute minimum as you run down to that end, that the area blows up in the neighborhood of that absolute minimum? Is that possible? And it seems not possible. You imagine, how is it possible for the area to blow up? You say, well, we just sort of say, we expect it to be sort of sliding around in sort of slices like this. But if you have these sort of slices, your minimum is down below that. So you might say, no, drop down to the minimum. You say, oh, no, I can't do that. Now I have to sort of come in sort of some other path. But if I come in some other path near that minimum, you kind of expect it to be the case. The curve is now sort of mostly horizontal. But if you have a lot of horizontal area, that's controlled by having a priori bounds on this. That can't happen. So it has to then be vertical. But if it's vertical, then you kind of expect it to extend down below the minimum and give you a contradiction. And so this was like the first component, the first idea, I guess, the first step to sort of say, something's not right here. There must be something kind of interesting. And so that was the first theorem that we proved. Which is essentially to say that if and I'm going to be sloppy just to save time a little bit here. So even if the case that your omega energy is bounded, so we kind of move outside of the category of just sort of considering curves that are coming from this sort of Gromov type degeneration, the Gromov next type degeneration. If this quantity, you consider curves more generally, which come down to a minimum, then they can be complicated. Right, they can have genus, they can have multiple positive ends in some reasonable sense. And you focus, so this height here, for instance, is A naught, and this height here is A naught plus R, right? Then there exists some large constant C, such that the integral of U star dA wedge lambda plus omega is less than C in this region, which is then A naught up to A naught plus R, and then I look at A inverse on this quantity here. And so what am I saying? C depends on R. So yeah, C depends on R. C depends on R and all the ambient geometry. So that means your J and your lambda, your omega, the corresponding Riemannian metric you get, and it definitely depends on R. It does not depend on A naught. Everything's sort of translation variant anyway, and it doesn't depend on the curve. And so what this says is that near this minimum, area can't get arbitrarily large. In fact, near the minimum, as long as you stay in this sort of compact distance away from that minimum, you do in fact have area bounds. Right? Now, if you move further away, you still have area bounds, but that area sort of, the bound gets much larger. Move further away, larger, larger, larger. Does that make sense? Oh yeah, it depends on E0 as well. It depends on E0, sorry. Yeah, so this one does not depend on genus. The omega energy does depend, but that can be on genus, but that can be removed. So C, I should say, is, maybe if I want to be precise, then C depends on this, it depends on R, it depends on the associated Riemannian metric J, lambda, and omega. Then that's it. And so it does depend on you. Okay, so that at least sort of says, okay, that's sort of good news. That sort of tells me, okay, that this weird scenario can't happen. Well, I suppose I can sort of poll the audience. So does this seem at this point? This should seem at this point, okay, that's slightly interesting. But does it strike you as sort of really interesting? Like, would you be excited when you saw this result? Okay. Okay. No, I think it's kind of an interesting question, right? Because it relies on this other idea. And I'm polling you just to.